Okay, so that was the bulk modulus. What about our other constant? What about the shear modulus? That was the other item that we started off talking about. So this is what relates the shear strain and the shear stress. It has to do with the change in shape of our material. And let's talk about some more circles. So I'm going to draw a circle here. Let's do that in blue. Okay, there's my first circle. Draw some axes on here for you. This is my stress circle. Okay, so we're in a state of pure shear. And what does that mean? It means that our circle is going to be centered at the origin. There is my normal stress. Do my best here. Here is my shear stress. Okay, and this is going to be in a state of pure shear. So there's that, and like that. And now let's think about how our strain picture. So I'll draw that over here, and let's use a different color. Let's use this light purple. Okay, let's draw that guy over here. And we will have another axis here. Again, this is going to be a pure shear state. So if that's my normal strain, we're going to also be centered at the origin in the strain space here. So this is going to be gamma over 2. And if we have this picture, this point here, if we apply some amount, we're going to assume that we're in the XY plane, just because it'll be easier to talk about. But you can imagine we could do this in any of the 3 planes. This guy is going to be tau xy. And if we orient our square this way, we'll have a state of pure shear, right? Now that we've done all of this stress transformation, you know that you could also orient the square. I would have to take my original orientation and rotate it an angle of 90 degrees on the circle, which would be a 45-degree rotation on the square. And if I did that, I would end up getting principal stresses, and they would look something like this. Okay, and so now I would see a sigma 1 here and a sigma 2 there. Okay, that's my stress picture. What about my strain picture now? So if I have tau xy, I know that my shear, so that would be gamma xy, is just going to be equal to tau xy, the shear stress, divided by the shear modulus, right? That was from before. And so if I go and look at my Mohr circle in strain, all I need to do to figure out this value, so at the very top there, is take that value, gamma xy, and divide it by 2. So this point here is going to be gamma xy over 2, which is equal to tau xy over 2g. There we go. Now the other thing I might want to know is what is the principal strain? Well, I could figure that out from my principal stresses. So let's write those out here. So if we think about the top of our circle, that would be our pure shear case. And we said that gamma xy is equal to tau xy over g, the shear modulus. Now we could also think about our principal stress state. There Sorry about that. Okay, and so what I want to figure out is what epsilon 1 is. So that's my principal strain. Well, we have some equations for that, right? If we think about, if we go back to the equations we derived for uniaxial stress and strain, we could do that for any orientation, including our principal orientation. So this would end up looking like 1 over E, the elastic modulus, times the stress that's also in that direction, which would be sigma 1. And then we would need to subtract off nu times sigma 2 and plus sigma 3. So those would be the stresses in the other two directions. And if we think about our principal stress state here, if we think about just a 2D or pure shear, what is sigma 3 going to end up being? It's going to be in the middle. It's going to be 0. So we can get rid of that, and we can set this stuff here equal to 1 over the elastic modulus times sigma 1 minus the Poisson's ratio times sigma 2. Okay, so now the key is to think about a couple of different things here. So we have some information about the locations on and the size of this Mohr circle in stress. We have some different information about the size of this Mohr circle on the right. And the thing that I'm going to take advantage of here is we know the radius of each of these Mohr circle. And what that's going to allow us to do is relate things that are happening on the principal axis with the things that are happening on the pure shear axis. So I'm going to start with strain. Okay, so I'm going to say the radius of the strain Mohr circle, which I'm just going to give some arbitrary name. I'm going to call it the radius epsilon, so we know it's strain. We said that was going to be equal to tau xy over 2g, right? That's the distance from here to there. And we also know it's the distance from here to there, right? And if that's the truth, then all we need to do is put in epsilon 1 here. That's 1 over E times sigma 1 minus nu, Poisson's ratio, times sigma 2. Now I can think about the same thing for stress. So this would be the picture on the left. And if I look at this picture on the left, I can think about the radius of the Mohr circle in the stress picture. So I'm going to give that an arbitrary name, call it radius sigma, just to make sure we don't confuse those two. And the radius and the sigma is going to be equal to tau xy, right? That's the distance from here to there. But it's also going to be equal to the distance from 0 to sigma 1 and the distance from 0 to sigma 2. So it's also going to be equal to sigma 1. It's also going to be equal to sigma 2. And so now, armed with this information, if I go back to this expression up top, so I'll underline this guy here. We know we have to deal with those guys there. And we can write this new expression. So tau xy over 2g equals to 1 over the elastic modulus and times, now we're going to use these equalities. So now we have tau xy minus nu, Poisson's ratio, tau xy again. And you can see that I can cancel all of those tau xy's. And I can get that G is going to be equal to the elastic modulus divided by 2 times 1 plus Poisson's ratio. And so there you go. Just like before, we have a relationship here. This is the shear modulus. Here's the elastic modulus. Here is Poisson's ratio. So now we have a way to go from our shear modulus and bulk modulus to our elastic modulus and Poisson's ratio, and vice versa.